Well, hello again. I've got two topics for you today. First, uniform angular acceleration equations, and then the relation between torque and angular acceleration. So first, the uniform angular acceleration equations. So when we have something that can spin, like say a disc like this, and we can express where it is and its spin by some angle theta, and it can spin with some omega. That spin, it may be able to speed up and slow down so that omega can change, and if the omega changes, that change is expressed by some angular acceleration alpha. So omega is the change in theta with time, and alpha is the change in omega with time. So if it speeds up really fast, that alpha is big. If it speeds up really slowly, that alpha is small. Now we've seen already, when we started earlier in the semester, uniform acceleration equations for like a baseball being dropped or a car merging onto a highway. So we saw earlier equations: V is V naught plus AT, X is X naught plus V naught T plus 1/2 AT squared, and V squared is V naught squared plus 2A X minus X naught. Now there are analogous equations for rotation. So this is for something, moving through space, like a car speeding up to get on a highway. Now we're going to talk about the analogous equations for something speeding up or slowing down in its spin. So V goes to omega, A goes to alpha, and X goes to theta. So whereas we had this equation before, we've now got omega is omega naught plus alpha t. So this is how fast it's spinning. That's how fast it speeds up or slows down its spin. Theta naught is almost always zero, so I'm just going to leave it out. So omega naught t plus 1/2 alpha t squared. And here, omega squared is omega naught squared plus 2 alpha, and again, theta naught's almost always zero, so I'm just going to call that theta. And those are equivalent, or not equivalent, or analogous angular equations for uniform angular acceleration. They look a little weird because they're using these Greek characters, but they're not really not much more difficult to use than these equations were. Sometimes we have to relate the two. If we have, say, something out on the edge at some radius r, and we want to know when this is spinning at some omega, how fast is this going with some v, say, and so we might need to know the relationship between the two, and we know that arc length is S is r theta, V tangential is r omega, and A tangential is r alpha. And those are the equations that allow us to move back and forth between, say, tangential velocity and angular velocity, tangential acceleration, angular acceleration, distance traveled, and angle. So let me just do an example. I think you'll see it's fairly straightforward. And everyone's seen a washing machine, so my example is going to be a washing machine with a sock on the rim. So I have a washing machine. It's got a radius of 0.3 meters, so 30 centimeters, and about like that. So the whole machine's about like that. And it's got a sock out here on the rim. That's supposed to be a sock. And this machine goes from rest to 40 revolutions per minute in 12 seconds. So we turn it on and it speeds up. It's going 0 and it starts getting faster and faster and faster, and it takes 12 seconds to speed up. So I've got these questions. What is alpha? How many revolutions does it make while it's speeding up? And how far does the sock travel? So that's just to practice these equations. So first, what is alpha? I need an equation with alpha in it. But all three of our new uniform equations have alpha in them. So I need one with time. These two have time because I was given the 12 seconds. This is the one that has speed in it, and I was given 40 revolutions per minute, so I'm going to use that one. Omega is omega naught plus alpha t. It started from rest, so omega naught is 0. Now in your homework and in your assignments, that may not always be true. It's not omega naught is always 0. If this had already been spinning and slowing down, then this would not have been 0. So alpha is omega over t. I need omega. Omega is 40 revolutions per minute. I need to convert it to radians per second for my equations to work, times a minute per 60 seconds, times 2 pi radians per revolution. And that is 4.19 radians per second. So alpha is 4.19 radians per second divided by the 12 seconds. 0.349 radians per second squared. That's how rapidly it was speeding up. So this alpha is 0.349 radians, it's supposed to be radians, per second squared. Notice I did have to use radians. I had to convert from the revolutions per minute to radians per second. There are ways around that, but it's just safest if you do it. How many revolutions? What I'm going to do there, I'm going to find theta. I'm going to find the angle that it spun through, because that's what my equation can tell me. And then I'm going to convert that angle from radians to revolutions. So theta is omega naught t plus 1/2 alpha t squared. Omega naught is again 0 here in my example, but it won't always be 0. It's 1/2 times 0.349 radians per second squared times my 12 seconds squared. So the angle that it rotated through is 25.1 radians. But I wanted revolutions, so times 1 revolution for every 2 pi radians. And that's 4 revolutions. So it only went around 4 times while it was speeding up. Then how far does the sock travel? So the sock is out here on the rim, traveling through some S, through some arc length. And S is r theta. So that is, r is 0.3 meters times theta was 25.1 radians. So S is 7.5 meters, 7.53 meters. That's how far the sock went. So there's my example. You've done similar things earlier, just using the uniform A equations. Now we're using the uniform alpha equations. The same sorts of ideas. You find out what do you know, what do you want to know, and you find an equation with that in it, and you solve for the part that you don't know. Do remember to put your calculator in radians, and remember to use units of radians, radians per second, and radians per second squared. Okay, so that settles the first topic. Let's move on to the second topic of the day, which is the relationship between torque and angular acceleration. So, torque and angular acceleration. So let me introduce it in a simple case here. Suppose I have an object like a mass m that's at some radius r, and it's just being sped up with some tangential force like this. I know that that force will accelerate that object with F equals ma. I can multiply both sides of this equation by r. Because, why am I doing that? Because this tells me F times r is a torque if this force is perpendicular. And I'm trying to get an understanding of torque. But I also know that if I'm describing this, where this particle is, not in terms of where it is in space by x, but in terms of some theta and some omega and some alpha, I know that this A is R alpha. So I've got FR is M R alpha. I'm using the capital R and the little r. Those are the same R. This is a little r. So F times R is mR squared times alpha. But this is torque, and this is something mR squared times alpha. But I said I was looking for a relationship between torque and alpha, and I've got it here. So I'm going to define this as something new. I'm going to call this I. I'm going to call this the rotational inertia, or it's often called the moment of inertia. There are mathematical reasons for that, for calling it a moment. So I, for this particle moving in a circle, is just mR squared. Again, the little r and the big R mean the same thing here. So I've now got torque is I alpha, where this I for a particle is just mR squared. So if this particle had a mass of 2 kilograms and this R was 2 meters, then this I would be 2 kilograms times 2 meters squared. 2 times 2 is 4, times 2 is 8, would be 8 kilogram meters squared would be the moment of inertia of that particle. And then we could relate the torque on that particle to its angular acceleration through that moment of inertia from torque is I alpha. We don't usually do that for just particles. We usually don't think about a particle like this, but we think about, for something rotating like this, we think about like a disk or a sphere or a planet or a ring or something like that. So for those cases, we have to be able to calculate this moment of inertia. And for those cases, it's not a simple mR squared. We still have the relation for something torque equals I alpha, but then this moment of inertia is something different, and it takes calculus to compute it. So we're just going to make a table. So for moment of inertia, so for a hoop, for example, something like that, with some radius r, the moment of inertia is mR squared. Now you couldn't possibly just know that. That comes from, again, from calculus. For a cylinder or disk, so we've just got something flat like this, like a penny, then I is 1/2 mR squared. For a sphere, that's kind of hard for me to draw. I hope you get the idea. So for a solid sphere, it has to be solid, then I is 2/5 mr squared. For a long rod, we get two answers depending on where the axis of rotation is. If the axis is in the center, so for a rod with the axis here, and the rod has a length L, I is 1/12 ml squared. But if we rotate it about the end, like that, where it's got a length L, I is 1/3 ml squared. Now I would give you a table of these on a quiz, and you'd have a table available in your homework. There's one in the book. And I would not expect you to memorize these. I don't have them memorized. I look them up when I need them. But I would expect you to understand conceptually something about them. Notice there's always a mass, and there's always a length squared, either an R squared or an L squared. So this tells me something conceptually, because again, this I tells me something about torque and alpha. It's inertia, it's resistance to rotational acceleration. I, moment of inertia is a measure of an object's resistance to rotational acceleration. The bigger that number is, the harder it is to make that thing spin, or if it's already spinning, the harder it is to slow it down. So the more massive something is, the harder it is to make it spin. But more importantly, the bigger that radius is, has an even bigger effect because it's squared. So as the mass gets further from the axis, it gets really hard to make something spin. Or if it's already spinning, it's really hard to stop it spinning because of this square. So if I double the mass here or anywhere, I get twice the moment of inertia. But notice if I double the radius, I get 4 times the moment of inertia. It gets 4 times as hard to spin it. If I triple the radius, it gets 9 times as hard to spin it, because the 3 would get squared. So where you put the mass makes a great deal of difference in moment of inertia. It makes a big difference in trying to make something spin, speeding it up or slowing it down. All right, let me do an example for you, and then we'll call it a day. You can practice all this in your homework. Okay. Example. Suppose I have a grindstone, like you would sharpen knives or something with. And it's 20 kilograms. And it has a radius of 20 centimeters, and I want to know what torque needed to accelerate it from rest to 2 revolutions per second in 8 seconds. All right, I've got one equation. Torque equals I alpha. So I'm going to have to use that. So I want to know torque. Clearly I need I and I need alpha. To get alpha, I'm going to have to use my new equations I just learned, my uniform angular acceleration equations. So omega is omega naught plus alpha t. Omega naught was 0. Omega is 2 revolutions per second times 2 pi radians per revolution is 12.6 radians per second. So omega, oh, I just said what that is, 12.6 radians per second. So alpha is omega over t, 12.6 radians per second divided by 8 seconds is 1.57 radians per second squared. So now I know alpha. I need I. To get I have to go to that table and find out what is I for a disk. I for a disk is 1/2 mr squared. So again, you look that up in a table. That's 1/2 times the 20 kilograms times the 0.2 meters squared. So that is 0.4 kilogram meter squared. Now I know alpha, I know I, the torque is very easy. I alpha is 0.4 kilogram meter squared times 1.57 radians per second squared. That's 0.628. The units come out as Newton meters. That's not obvious, but they do. So there's the torque. That was my question. What if I want to know the force? Suppose I apply a tangential force here like that. That was supposed to show that it was tangential. So I now know torque is force times radius. So the force would be the torque over the radius. That was supposed to be an R. So my torque was 0.628 Newton meters. The radius was 0.20 meters. So the force would be 3.14 newtons. So if I apply 3.14 newtons for 8 seconds, this 20 kilogram stone will accelerate up to 2 revolutions a second. That's a lot. You should probably practice that. You should probably work through that again, each step, until you're sure you understand each part. Because it's got torque equals I alpha in it. It's got uniform angular acceleration omega in it. It's got unit conversions in it. We had to find alpha. We had to use a table to find I. Once we had the torque, we had to use torque as the force times the radius to get the force. There's so much in this problem. Work it over and over, making sure you understand each step, and then you'll really be understanding a lot about rotational motion. So you'll get there. Don't give up. See you soon.